deep groove between the temporal lobe below and the frontal and occipital and parietal lobes above. This is called the lateral sulcus, or because it's deep, some books will refer to it as the lateral fissure. Either one is correct. Either one is okay. They're used interchangeably.
So every fissure is a sulcus, but not every sulcus is a fissure.
Every fissure is a deep sulcus. Now, note that the cerebellum sits right below the occipital lobe. That's where it's situated. Now let's talk about the cerebral cortex. It says the cortex is the seat of conscious awareness. For us to be fully cognitive with respect to some type of sensory input, those sensory impulses have to reach the cortex. All of the higher thought processes are the result of electrical activity within the cortex. Furthermore, when we initiate voluntary activity, those impulses are generated within the cortex. Okay? So it says the cortex allows us to be aware of sensations, to initiate voluntary movements, and also to communicate. So language function is housed within the cortical tissue. In fact, from a functional standpoint, there are three types of functional areas within the cortex: motor areas, sensory areas, and association areas. We're going to talk about these. And then finally, something I think most of you are aware of is that each hemisphere controls and receives sensation from the contralateral half of the body. You know, the nervous system is amazing. Watch very closely what I'm going to do. Everybody's looking? Did you see that? In order to initiate that movement on the right side of the body, I had to trigger electrical impulses within the left hemisphere. The left hemisphere controls the opposite or contralateral side of the body.
So strokes are normally on the right side of the brain?
Okay, they can be on either side.
Maybe on either side, but it's... Then why is it always like, why do they normally like... Never mind. I don't know where I was going with that.
Now, let's suppose Jordan left some tacks facing up on the surface of this desk.
Always.
And I went to lean onto the desk. Okay? And I stabbed myself, the palm of my hand, and I felt pain. Okay? Well, those sensory impulses would come up the right arm and then cross over into the left hemisphere and reach the sensory cortex of the left hemisphere for me to appreciate that as pain and for me to be able to localize it to my hand. So opposites. Opposites. It's like the scarecrow.
Dr. Bennett,
Yes?
where is the sensory cortex located?
We're going to talk about that. Just hang on. It's an exciting question, but we're going to get to it. Now, this gyrus along the posterior aspect of the frontal lobe, sitting right in front of the central sulcus, in other words, this one right here on either side, this one we're going to call the precentral gyrus. So you have a right precentral gyrus and a left precentral gyrus. And that precentral gyrus is part of the frontal lobe. It sits along the posterior-most aspect. Okay. I'm going to get a little ahead of myself, but I want to point out the fact that there's a gyrus that sits behind or posterior to the central sulcus. What do you think we call that gyrus? Oh, you guys are good. Yeah. Yes. Post-central
Setting us up for failure, Colin.
gyrus. These are two very, very important gyri. Okay? Now, it turns out that the precentral gyrus houses what's called the primary motor cortex. These are the cortical areas that control skeletal muscle movement. So the primary motor cortex is housed within the precentral gyrus. The neurons that are found within this primary motor cortex, many of them are shaped like pyramids. In other words, their cell body looks like this. They go around the nucleus like this, with the prominent nucleolus, and the axons are coming down like this. Okay? These cells that are found within the primary motor cortex and control skeletal muscle activity, they're called pyramidal cells. And again, it's based upon the fact that their cell bodies are shaped like a pyramid. Of course, these pyramidal cells located within the primary motor cortex are going to give rise to bundles of axons. And we can call these bundles of axons pyramidal tracts. These pyramidal tracts are carrying descending electrical impulses which are going to serve to initiate skeletal muscle activity. So the neurons within the primary motor cortex are called pyramidal cells, and their axons form pyramidal tracts. Now it says something very interesting. It says the body is spatially represented on each cortex, meaning along each primary motor cortex, with more neurons devoted to muscles that have more precise control. What regions of the body contain neurons or contain muscles? Let me say that. What regions of the body contain muscles that provide for precision movement? Face. And?
No.
What about the hands? Now the hands have small muscle groups that allow us to do things like sew and play piano and play jacks.
Jacks? Is that the?
Yeah.
Okay.
Yeah, I said it. Yeah. We're going to come back to that thought. But first, let's look at this color-coded brain here. On a color-coded brain, this region in red is the precentral gyrus. Yeah, this is the central sulcus. The precentral gyrus houses the primary motor cortex. See? Primary motor area. On the other hand, this area in green along the postcentral gyrus houses what's called the primary somatosensory cortex or area. If you want to call it the primary sensory area or cortex, that's fine also.
Wait, what is that called?
Primary somatosensory or primary sensory cortex, either one. The primary motor
The one doesn't have
cortex
somato.
is the area that initiates impulses that control skeletal muscle activity. The primary sensory cortex is the area that receives sensory information from the opposite side of the body. When that sensory information reaches the primary sensory cortex, it allows us to discriminate the type of sensory activity that's being sensed, whether it's, for instance, whether it's painful or whether it's a light touch or whether it's a vibration or a deep pain, and allows us to localize it. So primary motor cortex along the precentral gyrus, primary sensory or somatic sensory cortex along the postcentral gyrus. Now, earlier I said that the cortex can be divided into motor areas, sensory areas, and association areas. We're going to focus right now on motor areas. So, the primary motor cortex, of course, would be a motor area right here within the precentral gyrus. Let's look at this area in a frontal section. Here's a frontal section of the brain sliced through the precentral gyrus. Okay? If we look at this brain here, this red striped area and this solid red area represent the precentral gyrus. If I were to take this brain and slice it in the frontal plane like this, I would get an image that resembles this. And what they have done is superimposed upon the primary motor cortex what's called an homunculus. The homunculus is a little man.
That scares me.
Okay? And what the little man demonstrates is the areas of the primary motor cortex that control certain regions of the body. Okay? Notice that there is relatively more cortex devoted to control the muscles of the hand and face than is devoted, let's say, to the lower extremity on the trunk. And that's because the muscles of the face are capable of precision control. Same too holds true for the hand. Okay? Turns out this little man, his name is Hal. H-A-L. Okay. I'm going to draw a frontal section through the primary motor cortex, much like we would see if we were obtaining an MRI of the brain. Okay? It would look like this if it was taken in sections along the frontal plane. Now, if I saw a lesion in this area right here, let's say from a stroke, without even looking at the patient, I would suspect that the patient, and this is going to be the right side, this is going to be the left side, is going to have some left facial weakness. Okay? Why? Well, Hal. H-A-L. Head and neck, including the face. This area of the brain, primary motor cortex, controls the arm and hand. And then the medialmost aspect is the lower extremity or leg. So when we write Hal, we go from lateral to medial. Like this. Okay?
Arm.
Now, notice that Hal's cousin, another homunculus, also named Hal, is superimposed upon the primary sensory cortex. Okay? With regard to the sensory cortex, more neurons are devoted to areas of the body that have a higher concentration of sensory receptors. So the distribution of neurons is fairly similar. Because the hand has a high density of sensory receptors, then more of the primary sensory cortex is devoted to reception of impulses from the hand than to other regions. Same thing holds true for the face. A higher density of sensory receptors, so more of the primary motor sensory cortex is devoted to the face. Whereas you notice here within the lower extremities, even though this is a larger region of the body, the concentration of receptors in that region is less than what we'd find in the hands or in the face.
So, like on the practical, would you give us an MRI with a stroke and tell us what?
Possibly, yeah. Yeah, I wouldn't rule that out. How many people here have played baseball before? Okay. So you know if you're standing up at the plate and you're about to bat and the pitcher's throwing the ball inside, okay, are you going to put your face in front of the ball? No, that's the moneymaker. That has a high density of sensory receptors. That's going to hurt. They always tell you instead to turn your body in. So it hits you in the back or the butt. Why? It's going to hurt less. Fewer sensory receptors. So what I've done is taken the liberty of putting Al's name here. Okay. Of course, if you have a lesion here, where's the weakness going to be? It's going to be on the right side or the left side? It's going to be on the left side. I'm sorry, the right side. Right side. When you look at a scan, you're always looking at it as if the patient is facing you. So this would be the left hemisphere that controls the right side of the body. Now, we said that this primary motor cortex within this gray matter houses pyramidal cells that are grouped into nuclei. Those pyramidal tracts are going to descend down into the white matter and converge here within the internal capsule. The internal capsule is going to carry those pyramidal tracts down toward the brainstem. Okay. Now remember, these internal capsules are also going to carry ascending tracts, but right now we're focusing on motor areas. If I took a slice a little bit further behind this one, I would pick up part of the brainstem, so that we can see these internal capsules now that are carrying pyramidal tracts connect here with the brainstem. And if I could take just the right plane, I could show you where the brainstem is going to connect with the spinal cord. So those descending pyramidal tracts are going to carry motor information, take the cortex down into the spinal cord. Okay. Those axons being carried by those pyramidal tracts are eventually going to synapse, okay, with a second group of neurons that will ultimately then carry that impulse out towards skeletal muscle. If you connect 2 and 2, what I just said is that somatic motor pathways that provide innervation to skeletal muscle, are 2 neuron pathways. The first neuron is carried by